Learning objectives. In this chapter, the user would learn the following in detail: Laplace transform, inverse transform, linearity, shifting, transforms of derivative and integrals, differential equations, convolution and integral equations, Fourier series, integrals and transforms. In that, periodic functions, trigonometric series, Fourier series, forced oscillations, Fourier transforms. Differential equations. Ordinary differential equation. Introduction. Differential equations are of fundamental importance in engineering mathematics because many physical laws and relations appear mathematically in the form of such equations. An ordinary differential equation is an equation that contains one or several derivatives of an unknown. Higher order linear differential equations with constant coefficients. A general form of linear differential equations of nth order with constant coefficient is d power ny divided by dx power n plus k1 into d power n minus 1 y divided by dx power n minus 1 plus k2 into d power n minus 2 y divided by dx power n minus 2 plus etc. plus kny equal to x is called equation number 1, where k1, k2, etc. kn are constants. The equation 1 can also be written in the form of d power n plus k1 into d power n minus 1 plus etc. kn into y equal to x. Note, point number 1, 1 by d into x equal to integral x into dx. Number 2, 1 by d minus a into x equal to e power ax integral x into e power minus ax dx. Number 3, 1 by d plus a into x equal to e power minus ax integral x into e power ax dx. The general form of the linear differential equation of second order is d square y by dx square plus p into dy by dx plus qy equal to r, where p and q are constants and r is a function of x or constant. Subdivision 2. Differential operators. The symbol capital D stands for the operation of differential, that is, capital dy equal to dy by dx, capital D square y equal to d square y by dx square. We no need to use capital D and then small d like this. Who learning this chapter, they can easily understand. We have to put capital D here, we have to use small d here. 1 by d stands for the operation of integration. 1 by d square stands for the operation of integration twice. d square y by dx square plus p into dy by dx plus qy equal to r can be written in the operator form. d square y plus p dy plus qy equal to r, or d square plus pd plus q into y equal to r. Complete solution is y equal to complementary function plus particular integral. To find the complementary functions, we have to see the tabular column very carefully. Roots of auxiliary equation and then complementary function. Serial number 1. Roots are real and different, m1, m2. That means m1 not equal to m2. Then the complementary function is a e power m1x plus b e power m2x. Number 2. Roots are real and equal, m1 equal to m2 equal to m say. Then the complementary function ax plus b into e power mx or a plus bx e power mx. Then serial number 3. The roots are imaginary, alpha plus or minus I beta. Then the complementary function for this e power alpha x into a cos beta x plus b sin beta x. To find the particular integral, pi equal to 1 by f of d into x. E power ax stands for x, then the particular integral equal to 1 by f of d into e power ax equal to e power ax into 1 by f of a, where f of a not equal to 0, equal to x into e power ax into 1 by f dash of a equal to 0, f dash of a not equal to 0, equal to x square into e power ax into 1 by f double dash of a, f of a equal to 0, f dash of a equal to 0, f double dash of a not equal to 0. Serial number 2, x power n stands for x, then particular integral equal to 1 by f of d into x power n equal to f of d whole power minus 1 into x power n. Expand f of d whole power minus 1 and then operate. That is serial number 3. Sin ax or cos ax stands for x, then pi equal to 1 by f of d into cos ax or sin ax. Replace d square by minus a square. Then serial number 4, e power x into pi of x stands for x. Pi equal to 1 by f of d into e power x into pi of x equal to e power x into 1 by f of d plus a into pi of x. Result, subdivision 1, 1 by d minus a into pi of x equal to e power ax into integral e power minus ax into pi of x dx. Subdivision 2, 1 by d plus a into pi of x equal to e power minus ax into integral e power ax pi of x dx. Example 1. Solve d square minus 5d plus 6 into y equal to 0. Solution. Given d square minus 5d plus 6 into y equal to 0, the auxiliary equation is m square minus 5m plus 6 equal to 0, that is m minus 3 into m minus 2 equal to 0. Using factorization, we will get, that is m equal to 2, m equal to 3, cf equal to a e power 2x plus b e power 3x. Thus the general solution is given by y equal to a into e power 2x plus b into e power 3x. Example 2. Solve d square minus 4d plus 13 into y equal to e power 2x. Solution. Given d square minus 4d plus 13 into y equal to e power 2x, the auxiliary equation is m square minus 4m plus 13 equal to 0. M equal to 4 plus or minus square root of 16 minus 52 divided by 2 equal to 4 plus or minus square root of minus 36 divided by 2 equal to 4 plus or minus 6i divided by 2 equal to 2 plus or minus 3i. Then the complementary function equal to e power 2x into a cos 3x plus b sin 3x. Pi equal to 1 divided by d square minus 4d plus 13 into e power 2x equal to 1 by 4 minus 8 plus 13 into e power 2x equal to 1 by 9 into e power 2x. Y equal to cf plus pi. Y equal to e power 2x into a cos 3x plus b sin 3x plus 1 by 9 e power 2x. Example 3. Find the pi of d square plus 4 equal to cos 2x. Solution. Given d square plus 4 equal to cos 2x. Pi equal to 1 by d square plus 4 into cos 2x. Replace d square by minus 2 square. Ordinary rules fails. Equal to 1 by minus 4 plus 4 into cos 2x. So we're getting 0 in the denominator. That's what the ordinary rules fails. Equal to x into 1 by 2d into cos 2x equal to x by 2 into integral cos 2x into dx equal to x by 2 into sin 2x divided by 2 equal to x by 4 into sin 2x. If we get d in the denominator, we have to integrate. If we get d in the numerator, we have to differentiate. Here we got d in the denominator, so we integrating. Example 3. Solve a d square minus 4d plus 4 into y equal to e power 2x plus cos 2x. Solution. Given d square minus 4d plus 4 into y equal to e power 2x plus cos 2x. The auxiliary equation is m square minus 4m plus 4 equal to 0. Then m minus 2 whole square equal to 0. By factorization we are getting m equal to 2 comma 2. Complementary function equal to ax plus b into e power 2x. pi1 equal to, that is called particular integral 1 equal to 1 divided by d square minus 4d plus 4 into e power 2x. Replace d by 2. equal to 1 by 4 minus 8 plus 4 into e power 2x equal to 1 by 0 into e power 2x. Here the ordinary rules fails. Equal to x into 1 divided by 2d minus 4 into e power 2x. Again replace d by 2 equal to x into 1 by 4 minus 4 into e power 2x equal to x into 1 by 0 into e power 2x. The ordinary rules fails. Equal to x square by 2 into e power 2x. One thing we have to notice it very clearly. What is when the ordinary rules fails? If we getting the denominator as 0, we just want to put one x in the numerator and then we have to differentiate it. After differentiating, again we getting 0 means again we have to put one x in the numerator and then we have to put one 2 in the down. Pi2 equal to 1 divided by d square minus 4d plus 4 into cos 2x. Replace d square by minus 2 square equal to 1 divided by minus 2 square minus 4d plus 4 into cos 2x equal to 1 by minus 4d into cos 2x equal to minus 1 by 4 into sin 2x divided by 2 equal to minus sin 2x divided by 8. Y equal to CF plus PI1 plus PI2 equal to AX plus B into e power 2x plus x square into 1 by 2 into e power 2x minus sin 2x divided by 8. Example 4. Solve d cube plus 8 into y equal to x power 4 plus 2x plus 1. The auxiliary equation is m cube plus 8 equal to 0. M plus 2 into m square minus 2m plus 4 equal to 0. Then m equal to minus 2 or m square minus 2m plus 4 equal to 0. M equal to minus 2 or m equal to 2 plus or minus square root of 4 minus 16 divided by 2. M equal to minus 2 or m equal to 2 plus or minus I 2 root 3 divided by 2. M equal to minus 2 or m equal to 1 plus or minus I root 3. CF equal to a into e power minus 2x plus e power x into b cos root 3x plus c sin root 3x. Pi equal to 1 by d cube minus 8 into x power 4 plus 2x plus 1 equal to 1 divided by 8 into 1 plus d cube divided by 8 into x power 4 plus 2x plus 1 equal to 1 by 8 into 1 plus d cube divided by 8 whole power minus 1 into x power 4 plus 2x plus 1 equal to 1 by 8 into 1 minus d cube divided by 8 plus etc. into x power 4 plus 2x plus 1 equal to 1 by 8 into x power 4 plus 2x plus 1 minus 24x by 8 equal to 1 by 8 into x power 4 plus 2x plus 1 minus 3x equal to 1 by 8 into x power 4 minus x plus 1. Y equal to CF plus PI. CF equal to a into e power minus 2x plus e power x into b cos root 3x plus c sin root 3x plus 1 by 8 into x power 4 minus x plus 1. Example 5. Obtain the particular integral of d square minus 2d plus 5 into y equal to e power x cos 2x. Pi equal to 1 divided by d square minus 2d plus 5 into e power x cos 2x. Replace d by d plus 1 equal to 1 divided by d plus 1 whole square minus 2 into d plus 1 plus 5 into e power x into cos 2x equal to 1 divided by d square plus 2d plus 1 minus 2d minus 2 plus 5 into e power x cos 2x equal to 1 divided by d square plus 4 e power x into cos 2x equal to 1 by minus 4 plus 4 into e power x cos 2x equal to 1 by 2d into x into e power x into cos 2x equal to x into e power x divided by 2 integral cos 2x into dx equal to x into e power x divided by 2 into sin 2x by 2 equal to x into e power x into sin 2x divided by 4. Example 6. Solve d square minus 2d plus 5 into y equal to x into e power x into sin x. Solution given d square minus 2d plus 5 into y equal to x into e power x into sin x. The auxiliary equation is m square minus 2m plus 1 equal to 0. M equal to 1, 1 by using factorization method. CF equal to a plus bx into e power x. Pi equal to 1 divided by d square minus 2d plus 1 into x into e power x sin x equal to 1 divided by d plus 1 the whole square minus 2 into d plus 1 into x into e power x sin x equal to e power x into 1 divided by d square plus 2d plus 1 minus 2d minus 2 plus 1 into x sin x equal to e power x into 1 by d square into x into sin x equal to e power x into x into 1 by d square into sin x minus e power x into 2d by d square the whole square into sin x equal to e power x into sin x by minus 1 minus e power x into 2d by minus 1 the whole square into sin x equal to e power x into minus sin x minus 2 into e power x into cos x equal to minus e power x into x sin x plus 2 cos x. Y equal to CF plus PI. Y equal to a plus bx into e power x minus e power x into x sin x plus 2 cos x. Example 7. Solve d square minus 6d plus 9 into y equal to 6 into e power 3x plus 7 into e power minus 2x minus log 2. Solution d square minus 6d plus 9 into y equal to 6 into e power 3x plus 7 into e power minus 2x minus log 2. The auxiliary equation is m square minus 6m plus 9 equal to 0. M minus 3 whole square equal to 0. Then m equal to 3, 3. CF equal to a plus bx into e power 3x. Pi1 equal to 1 by d minus 3 the whole square into 6 into e power 3x equal to 6 into 1 by 3 minus 3 the whole square into e power 3x. The ordinary method fails. So we differentiating equal to x into 1 divided by 2 into d minus 3 into 6 into e power 3x equal to 6x by 2 into 1 by 3 minus 3 into e power 3x. Again the ordinary method fails. Equal to x square by 2 into 6 into e power 3x equal to 3x squared into e power 3x. Pi2 equal to 1 by d minus 3 the whole square into 7 into e power minus 2x equal to 7 into 1 by minus 2 minus 3 the whole square into e power minus 2x equal to 7 by 25 e power minus 2x. Pi3 equal to 1 by d minus 3 the whole square into log 2 equal to 1 by 9 into log 2. Y equal to CF plus Pi1 plus Pi2 plus Pi3 equal to a plus bx into e power 3x plus 3 into x square into e power 3x plus 7 by 25 into e power minus 2x plus 1 by 9 into log 2. Method of variation of parameters. This method is very useful in finding the general solution of the second order equation d square a by dx square plus a1 into dy by dx plus a2 into y equal to x is called equation number 1. The complementary function of equation number 1 cf equal to c1 into f1 plus c2 into f2 where f1 and f2 are functions of x. Then pi equal to pf1 plus qf2 p equal to minus integral f2x divided by f1 f2 dash minus f1 dash into f2 into dx. Q equal to integral f1x divided by f1 f2 dash minus f1 dash into f2 into dx. Y equal to c1 f1 plus c2 f2 plus pi. Example. Solve d square y by dx square plus 4y equal to 4 tan x. Given d square plus 4 into y equal to 4 tan x. The auxiliary equation is m square plus 4 equal to 0, m equal to plus or minus 2i, cf equal to a cos 2x plus b sin 2x. Here f1 equal to cos 2x, f1 dash equal to minus 2 sin 2x, f2 equal to sin 2x, f2 dash equal to 2 cos 2x. f1 f2 dash minus f1 dash f2 equal to 2 cos 2x into cos 2x minus sin 2x into minus 2 sin 2x equal to 2 into cos square 2x plus sin square 2x equal to 2. Pi equal to Pf1 plus Qf2. P equal to minus integral f2x divided by f1 into f2 dash minus f1 dash into f2 into dx. P equal to minus integral sin 2x into 4 tan 2x divided by 2 into dx equal to minus 2 integral sin square 2x divided by cos 2x into dx equal to minus 2 integral 1 minus cos square 2x divided by cos 2x into dx equal to minus 2 into integral secant 2x into dx minus cos 2x into dx equal to minus 2 into 1 by 2 log secant 2x plus tan 2x minus sin 2x divided by 2 equal to sin 2x minus log of secant 2x plus tan 2x. Q equal to f1x divided by f1 into f2 dash minus f1 dash into f2 into dx equal to integral cos 2x into 4 tan 2x divided by 2 into dx equal to 2 into integral sin 2x into dx equal to minus 2 into cos 2x divided by 2 equal to minus cos 2x. Pi equal to Pf1 plus Qf2 equal to cos 2x into sin 2x minus log secant 2x plus tan 2x minus cos 2x into sin 2x equal to minus cos 2x into log of secant 2x plus tan 2x. Y equal to Cf plus Pi equal to a cos 2x plus b sin 2x minus cos 2x into log secant 2x plus tan 2x. Problems based on Cauchy's type. Example 1. Solve x square into d square minus x into d plus 1 into y equal to 0. Solution. Given x square d square minus xd plus 1 into y equal to 0. We can learn x square into d square or x square d square and also x into d or xd. Better we follow the x square d square and xd. Put x equal to e power z, xd equal to d dash, log x equal to z, x square into d square equal to d dash into d dash minus 1. We just want to substitute whatever we written now. We mentioned very clearly x square into d square equal to d dash into d dash minus 1, x into d, that means xd equal to d dash into d dash minus 1 minus d dash plus 1 into y equal to 0. Then d dash square minus 2d dash plus 1 into y equal to 0. The auxiliary equation is m square minus 2m plus 1 equal to 0. Then m minus 1 the whole square equal to 0. Then we are getting m equal to 1 comma 1. Y equal to az plus b into e power z equal to a log x plus b into x equal to x into a log x plus b. Example 2. Solve x square d square minus 2xd minus 4 into y equal to x square plus 2 log x. Solution. Given x square d square minus 2xd minus 4 into y equal to x square plus 2 log x is called equation number 1. Put x equal to e power z. If you take log on both sides, we will get log x equal to z. Then xd equal to d dash, x square d square equal to d dash into d dash minus 1. D dash into d dash minus 1 minus 2d dash minus 4 equal to e power z whole square plus 2z. D dash square minus 3d dash minus 4 into y equal to e power z the whole square plus 2z. The auxiliary equation is m square minus 3m minus 4 equal to 0. M minus 4 into m plus 1 equal to 0. we are getting m equal to 4 comma minus 1. The complementary function is CF equal to a into e power minus z plus b into e power 4z equal to a into x power minus 1 plus b into x power 4. Pi1 equal to 1 divided by d dash square minus 3d dash minus 4 into e power 2z equal to 1 divided by 4 minus 6 minus 4 into e power 2z minus 1 by 6 into e power 2z equal to minus 1 by 6 into x square. Pi2 equal to 1 by d dash square minus 3d dash minus 4 into 2z equal to minus 2 by 4 into 1 by 1 minus d dash square minus 3d dash by 4 into z equal to minus 1 by 2 into 1 minus d dash square minus 3d dash by 4 plus etc. into z equal to minus 1 by 2 into z minus 3 by 4 equal to minus z by 2 plus 3 by 8 equal to minus 1 by 2 log x plus 3 by 8. Y equal to CF plus Pi1 plus Pi2 equal to a into x power minus 1 plus b into x power 4 minus 1 by 6 into x square minus 1 by 2 into log x plus 3 by 8. Example 3. Solve x square d square minus xd plus 1 into y equal to log x. Solution. Given x square d square minus xd plus 1 into y equal to log x. Put x equal to e power z. After putting log on both sides, we are getting log x equal to z, xd equal to d dash, x square d square equal to d dash into d dash minus 1, d dash into d dash minus 1 minus d dash minus 1 into y equal to z, d dash square minus d dash plus 1 into y equal to z, then d dash square minus 2d dash plus 1 into y equal to z, d dash minus 1 the whole square into y equal to z. The auxiliary equation is m minus 1 the whole square equal to 0, m equal to 1 comma 1 by using factorization method. CF equal to az plus b into e power z, a log x plus b into x. Pi equal to 1 by d dash minus 1 the whole square into z, 1 minus d dash whole power minus 2 into z equal to 1 plus 2d dash plus 3d dash square plus etc. into z equal to z plus 2 equal to log x plus 2. Y equal to CF plus Pi equal to a log x plus b into x plus log x plus 2. Example 4. Solve x cube d cube plus 2x square d square plus 2 equal to 10 into x plus 1 by x. Solution. Given x cube d cube plus 2x square d square plus 2 equal to 10 into x plus 1 by x. Put x equal to e power z. Log x equal to z after taking log on both sides. Xd equal to d dash. X square d square equal to d dash into d dash minus 1. X cube d cube equal to d dash into d dash minus 1 into d dash minus 2. Then we're going to substitute all the d dash in our equation. D dash into d dash minus 1 into d dash minus 2 plus 2 into d dash minus 1 plus 2 into y equal to 10 into e power z plus e power minus z. D dash cube minus 3d dash square plus 2d dash square minus 2d dash plus 2 into y equal to 10 into e power z plus e power minus z. Then d dash cube minus d dash square plus 2 into y equal to 10 into e power z plus e power minus z. The auxiliary equation is m cube minus m square plus 2 equal to 0. Then m plus 1 into m square minus 2m plus 2 equal to 0. M plus 1 equal to 0. If we put m plus 1 equal to 0, we will get m equal to minus 1. Then m square minus 2m plus 2 equal to 0. After solving this, we are getting m equal to 2 plus or minus square root of 4 minus 8 by 2 equal to 2 plus or minus square root of minus 4 by 2 equal to 2 plus or minus 2i by 2 equal to 1 plus or minus I. CF equal to a into e power minus z plus e power z into b into cos z plus c into sin z equal to a into x power minus 1 plus x into b cos log x plus c sin log x. Pa1 equal to 1 by d dash cube minus d dash square plus 2 into 10 into e power z equal to 10 into 1 by 1 minus 1 plus 2 into e power z equal to 10 into 1 by 2 into e power z equal to 5 into e power z equal to 5x. Pa2 equal to 1 by d dash cube minus d dash square plus 2 into 10 into e power minus z equal to 10 into 1 by minus 1 plus 2 into e power minus z. Here our ordinary method fails. Equal to 10 into z into 1 by 3 into d dash square minus 2 into d dash into e power minus z equal to 10z into 1 by 3 plus 2 into e power minus z equal to 10 into e power minus z into z equal to 10 into x power minus 1 into log x equal to 10 by x into log x. Y equal to cf plus pi1 plus pi2 equal to a into x power minus 1 plus x into b cos log x plus c sin log x plus 5x plus 10 by x into log x. Fourier series, integrals and transforms. Fourier series. Fourier has given a powerful technique of expressing a periodic function f of x of period 2L as a trigonometric series of the form f of x equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L, where a naught equal to 1 by L integral minus L to L f of x dx, then an equal to 1 by L integral minus L to L f of x into cos n pi x by L into dx, bn equal to 1 by L integral minus L to L f of x into sin n pi x by L into dx. However, such a form of f of x is not possible for a non-periodic function defined over an infinite interval. But an infinite series representation of f of x led Fourier to give an integral representation of f of x for periodic functions. Non-periodic functions could be assumed to have an infinite period. Dirichlet condition. Let f of x satisfy the following conditions called Dirichlet condition. Number 1. F of x is defined in the interval c less than x less than c plus 2L. Number 2. F of x and f dash of x are sectionally continuous in c less than x less than c plus 2L. That is, if the interval is subdivided into a finite number of subintervals, then in each of which the function is continuous. 3. F of x is periodic with period 2L, that is, f of x plus 2L equal to f of x. Fourier integral theorem. If f of x satisfies the above condition in every finite interval, and if integral minus infinity to plus infinity f of x dx is absolutely convergent, that is, integral minus infinity to plus infinity modulus of f of x dx is convergent, then at each point of the continuity x of f of x equal to 1 by 2 pi integral minus infinity to plus infinity, again integral minus infinity to plus infinity f of t into cos s into t minus x dt into ds. If f of x is defined in minus 1 less than x less than 1 and satisfies the Dirichlet condition, then we can write f of x as f of x equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L is called equation number 1, where a naught equal to 1 by L integral minus 1 to 1 f of x dx, an equal to 1 by L integral minus 1 to 1 f of x cos n pi x by L into dx, bn equal to 1 by L integral minus 1 to 1 f of x sin n pi x by L into dx. While treating t as dummy variable of integration, we will get a naught equal to 1 by L integral minus 1 to 1 f of t into dt, an equal to 1 by L integral minus 1 to 1 f of t into cos n pi t divided by L into dt, bn equal to 1 by L integral minus 1 to 1 f of t into sin n pi t divided by L into dt, f of x equal to 1 by pi integral 0 to infinity, again integral minus infinity to plus infinity, f of t into cos s into t minus x into ds into dt. The double integral is known as Fourier integral formula for f of x. Important results. The formula can be written as f of x equal to 1 by 2 pi integral minus infinity to plus infinity, again integral minus infinity to plus infinity, f of t into cos s of t minus x into dt into ds. Subdivision 2. By expanding the cosine term, we have f of x equal to 1 by pi integral 0 to infinity, integral minus infinity to plus infinity, f of t into cos st into cos sx plus sin st into sin sx into dt into ds equal to 1 by pi integral 0 to infinity cos sx into integral minus infinity to plus infinity f of t into cos st into dt plus sin sx into integral minus infinity to plus infinity f of t into sin st into dt into ds. First we integrating with respect to t. While we integrating with respect to t, we keeping the function with respect to s as constant. That's what we separated the integration there. Equal to 1 by pi integral 0 to infinity a of s into cos sx plus b of s into sin sx, where a of s equal to integral minus infinity to plus infinity f of t into cos st into dt, b of s equal to integral minus infinity to plus infinity f of t into sin st into dt. Fourier sine and cosine integrals. If f of x is an odd function, then a of s equal to integral minus infinity to plus infinity f of t into cos t into dt equal to 0, and b of s equal to integral minus infinity to plus infinity f of t into sin st into dt equal to 2 times of integral 0 to infinity f of t into sin st into dt. In that case, the Fourier integral formula 3 reduces to the form f of x equal to 1 by pi integral 0 to infinity b of s into sin sx dx, where b of s equal to 2 times of integral 0 to infinity f of t into sin st into dt. That is, f of x equal to 2 into 1 by pi into integral 0 to infinity sin sx into ds into integral 0 to infinity f of t into sin st into dt. This is called Fourier sine integral for an odd function f of x. Suppose f of x is an even function, then b of s equal to integral minus infinity to plus infinity f of t sin st into dt equal to 0. A of s equal to 2 times of integral 0 to infinity f of t into cos st into dt. Thus f of x equal to 1 by pi integral 0 to infinity a of s into cos sx into ds. Then again f of x equal to 2 into 1 by pi integral 0 to infinity cos sx into ds into integral 0 to infinity f of t into cos st into dt. This is called Fourier cosine integral for an even function f of x. Complex form of Fourier integral. The Fourier integral formula is f of x equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f of t into cos s of t minus x ds into dx. F of x equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f of t into e power is into t minus x plus e power minus is into t minus x divided by 2 into ds into dx equal to 1 by 2 pi integral 0 to infinity ds integral minus infinity to plus infinity f of t into e power is into t minus x plus e power minus is into t minus x divided by 2 into dt equal to 1 by 2 pi integral 0 to infinity ds integral minus infinity to plus infinity f of t into e power is into t minus x into dt plus 1 by 2 pi integral 0 to infinity ds into integral minus infinity to plus infinity f of t into e power minus is into t minus x into dt equal to 1 by 2 pi integral 0 to infinity into ds integral minus infinity to plus infinity f of t into e power is into t minus x into dt plus 1 by 2 pi integral 0 to infinity ds integral minus infinity to plus infinity f of t into e power minus is into t minus x into dt, replacing s by minus s in first integral, equal to 1 by 2 pi integral minus infinity to 0 ds integral minus infinity to plus infinity f of t into e power minus is into t minus x into dt plus 1 by 2 pi integral 0 to infinity ds into integral minus infinity to plus infinity f of t into e power minus is into t minus x into dt, equal to 1 by 2 pi integral minus infinity to plus infinity into ds integral minus infinity to plus infinity into f of t into e power minus is into t minus x into dt. This is called complex form of the Fourier integral. Fourier transform. The complex form of the Fourier integral is f of x equal to 1 by 2 pi integral minus infinity to plus infinity into ds integral minus infinity to plus infinity f of t into e power minus is into t minus x into dt, equal to 1 by 2 pi integral minus infinity to plus infinity e power minus isx into ds integral minus infinity to plus infinity e power ist into dt, equal to 1 by 2 pi integral minus infinity to plus infinity capital F of s into e power minus isx into ds, where capital F of s equal to integral minus infinity to plus infinity f of t e power ist into dt. The function capital F of s is called the Fourier transform of f of x. The function f of x is called the inverse Fourier transform of capital F of s. The Fourier transform of f of x is denoted by capital F of small f of x or f of s, and the inverse Fourier transform of f inverse of f of s, that means capital F inverse of capital F of s, that is f of s bar equal to integral minus infinity to plus infinity f of x into e power minus isx into dx. Inverse formula for complex Fourier transform. If f of s, that means capital F of s, is the Fourier transform of f of x, and if f of x satisfies the Dirichlet conditions in every finite interval minus L to L, and if integral minus infinity to plus infinity f of x into e power minus isx into dx is convergent, then at every point of continuity of f of x equal to 1 by 2 pi integral minus infinity to plus infinity capital F of s into e power minus isx into ds. That is capital F inverse of capital F of s equal to 1 by 2 pi integral minus infinity to plus infinity capital F of s into e power minus isx into ds. Result. The Fourier transform capital F of s and its inverse transform f of x can be written as capital F of x equal to 1 by 2 pi integral minus infinity to plus infinity f of t into e power ist into dt. F of x equal to 1 by square root of 2 pi integral minus infinity to plus infinity capital F of s into e power minus isx into ds. Fourier sine transform. The Fourier sine integral formula is f of x equal to 2 by pi integral 0 to infinity sin sx into ds integral 0 to infinity f of t into sin st into dt. Denote capital Fs of s equal to integral 0 to infinity f of t into sin st into dt. Then f of x equal to 2 by pi integral 0 to infinity fs of s sin sx into ds. Here fs of s, that means capital Fs of s equal to integral 0 to infinity f of t into sin st into dt is called the Fourier sine transform of capital Fs of s. Result. The Fourier sine transform Fs of capital S and its inverse f of x can also be written as Fs of s, that means capital Fs of s equal to square root of 2 by pi integral 0 to infinity f of t into sin st into dt. Then f of x equal to square root of 2 by pi integral 0 to infinity capital Fs of s sin sx into ds. Fourier cosine transform. The Fourier cosine integral formula is f of x equal to 2 by pi integral 0 to infinity cos sx into ds integral 0 to infinity f of t into cos st into dt. Denote fc of s equal to, that means capital Fc of s equal to integral 0 to infinity f of t into cos st into dt. Then f of x equal to 2 by pi integral 0 to infinity capital Fc of s cos sx into ds. Here capital Fc of s equal to 2 by pi integral 0 to infinity f of t into cos st into dt is called the Fourier cosine transform of f of x, and f of x equal to 2 by pi integral 0 to infinity fc of s into cos sx into ds is called the inverse Fourier cosine transform of fc of s, that means capital Fc of s. Result: the Fourier cosine transform capital Fc of s and its inverse f of x can also be written as capital Fc of s equal to square root of 2 by pi integral 0 to infinity f of t into sin st into dt. Then f of x equal to square root of 2 by pi integral 0 to infinity capital Fc of s sin sx into ds. Summary of results: Fourier integral theorem. F of x equal to 1 by 2 pi integral minus infinity to plus infinity f of t into cos s of t minus x into ds into dt. Fourier cosine formula: f of x equal to 2 by pi integral 0 to infinity cos sx into ds integral 0 to infinity f of t into cos st into dt. Fourier sine formula: f of x equal to 2 by pi integral 0 to infinity sin sx into ds integral 0 to infinity f of t into sin st into dt. Fourier transform: f of s equal to integral minus infinity to plus infinity f of x into e power isx into dx. Fourier inverse transform: f of x equal to 1 by 2 pi integral minus infinity to plus infinity capital F of s into e power minus isx into ds. Fourier cosine transform: capital Fc of s equal to integral 0 to infinity f of x cos sx into dx. Fourier inverse cosine transform: f of x equal to 2 by pi integral minus infinity to plus infinity capital Fc of s into cos sx into ds. Fourier sine transform: capital Fs of s equal to integral 0 to infinity f of x into sin sx into dx. Fourier inverse sine transform: f of x equal to 2 by pi integral 0 to infinity capital Fs of s sin sx into ds. Properties. Number 1. Linearity. Capital F of a into f of x plus b into g of x equal to a into capital F of s plus b into capital G of s. Number 2. Change of scale. If capital F of x equal to capital F of s, then capital F of ax equal to 1 by a f of s by a. If fs of f of ax equal to capital Fs of s, then capital Fs of f of ax equal to 1 by a fs of s by a. If capital Fc of f of x equal to capital Fc of s, then capital Fc of f of ax equal to 1 by a capital Fc of s by a. Third property, shifting. Capital F of x equal to capital F of s, then capital F of x plus a equal to e power isa into capital F of s. Number 4. Modulation. Capital F of x into cos ax equal to 1 by 2 capital F of s plus a plus capital F of s minus a. Fc of fx of cos ax equal to 1 by 2 into Fc of s plus a plus Fc of s minus a. Fs of f of x into sin ax equal to 1 by 2 into Fs of s plus a minus Fs of s minus a. Fs of f of x equal to Fs of s, then Fs of f of x sin ax equal to 1 by 2 into Fs of s minus a minus Fs of s plus a. Number 5. Derivatives. Capital F of f power n of x equal to minus is whole power n into capital F of s. Number 6. Capital F of x power n into f of x equal to minus I whole power n into capital F power n of s. 7. Capital F of integral 0 to x f of x into dx equal to minus I whole power n into capital F power n of s. Number 8. Capital F of x bar equal to capital F of minus s bar. Capital F of minus x bar equal to capital F of s bar. Number 9. Convolution theorem. Capital F of f into g equal to capital F of s into capital G of s. Number 10. Parseval's identity. Integral minus infinity to plus infinity modulus of f of x square into dx equal to 1 by 2 pi integral minus infinity to plus infinity capital F of s modulus square modulus of capital F of s square into ds. Example. Find the Fourier transform of f of x equal to x for modulus of x less than a, 0 for modulus of x greater than a. Solution. Capital F of small f of x equal to integral minus infinity to plus infinity e power isx into f of x into dx equal to integral minus infinity to minus a e power isx into f of x dx plus integral minus a to a e power isx into f of x dx plus integral a to infinity e power isx into f of x dx equal to integral minus a to a e power isx into f of x dx equal to integral minus a to a e power isx into x into dx equal to x into e power isx by is with limit minus a to a minus integral minus a to a e power isx by is into dx equal to x into e power isx by is with the limit minus a to a minus e power isx by is the whole square with the limit minus a to a. After applying the limits, we getting 1 by is into a into e power ias plus a into e power minus ias plus 1 by s square into e power ias minus e power minus ias equal to a divided by is into 2 cos as plus 1 by s square into 2i sin as equal to 2ai divided by s into cos as plus 2i sin as divided by s square equal to 2i into sin as minus as into cos as divided by s square. Example. Find the Fourier transform of f of x equal to e power iwx for a less than x less than b, 0 for x less than a, x greater than b. Solution. F of x equal to e power iwx for a less than x less than b, 0 for x less than a, x greater than b. Then capital F of small f of x equal to integral a to b e power isx into e power iwx into dx equal to integral a to b e power I into s plus w into x into dx equal to, after integrating we getting e power I of s plus w into x divided by I of s plus w with the limit a to b. After applying the limits, we getting e power I of s plus w into b minus e power I of s plus w into a divided by I of s plus w equal to I divided by s plus w into e power I of s plus w into a minus e power I of s plus w into b. Example. Find the Fourier transform of f of x equal to 0 for 0 less than x less than a, x for a less than or equal to x less than or equal to b, 0 for x greater than b. Solution. Capital F of small f of x equal to, we no need to say small f of x, it is very understandable. Better be saying capital F of x equal to integral a to b x into e power isx into dx equal to x into e power isx divided by is with limit a to b minus integral a to b e power isx by is into dx. Here we use the formula uv minus integral v du equal to 1 by is into b into e power isb minus a into e power isa minus e power isx by is square, that means is the whole square with the limit a to b. After applying the limits, we getting the final answer b into e power isb minus a into e power isa divided by is plus e power isb minus e power isa divided by s square. Example: find the Fourier cosine transform of f of x equal to cos x for 0 less than x less than a, 0 for x greater than a. Solution: capital FC of s equal to integral 0 to infinity f of x into cos sx into dx equal to integral 0 to a cos x into cos sx into dx equal to 1 by 2 into integral 0 to a cos of 1 plus s into x plus cos of 1 minus s into x into dx equal to 1 by 2 integral 0 to a sin of 1 plus s into x by 1 plus s sin of 1 minus s into x divided by 1 minus s with the limit 0 to a. After applying the limits, we getting 1 by 2 into sin of 1 plus s into a by 1 plus s plus sin of 1 minus s into a divided by 1 minus s. Example: find the sine transform of 1 by x into e power minus ax. Solution: f of x equal to 1 by x into e power minus ax. Capital Fs of f of x equal to integral 0 to infinity f of x into sin sx into dx equal to integral 0 to infinity e power minus ax into 1 by x into sin sx into dx. Differentiating with respect to s, d capital Fs by ds equal to, that means differentiation, equal to integral 0 to infinity e power minus ax into cos sx into ds equal to e power minus ax divided by a square plus s square into minus a cos sx plus s sin sx with the limit 0 to infinity equal to a by a square plus s square. After applying the limits, we getting this formula, that is d capital Fs by ds equal to a divided by a square plus s square. D capital F equal to ads by a square plus s square. Integrating capital Fs equal to tan inverse s by a plus c. When s equal to 0, Fs equal to 0. Therefore, from equation number 2, 0 equal to 0 plus c. Therefore, c equal to 0. Capital Fs equal to tan inverse s by a. Example: find the Fourier cosine and sine transformation of f of x equal to 1 for 0 less than x less than 1, 0 for x greater than or equal to 1. Solution: capital Fc of f of x equal to integral 0 to infinity f of x into cos sx into dx equal to integral 0 to 1 cos sx into dx equal to, after integrating we getting sin sx by s with the limit 0 to 1 equal to sin s by s. Capital Fs of f of x equal to integral 0 to infinity f of x into sin sx into dx equal to integral 0 to 1 sin sx into dx equal to minus cos sx by s with the limit 0 to 1 equal to 1 minus cos s by s. Example: use the sine inversion formula to obtain f of x if capital Fs equal to s by 1 plus s square. Solution: by inversion formula, f of x equal to 2 by pi integral 0 to infinity s by 1 plus s square into sin sx into ds equal to 2 by pi integral 0 to infinity s by 1 plus s square sin sx into ds equal to 2 by pi integral 0 to infinity s square plus 1 minus 1 divided by 1 plus s square into sin sx by s into ds equal to 2 by pi integral 0 to infinity 1 minus 1 by 1 plus s square into sin sx by s into ds equal to 2 by pi integral 0 to infinity sin sx by s into ds minus 2 by pi integral 0 to infinity 1 by s into 1 plus s square into sin sx ds equal to 2 by pi into pi by 2 minus 2 by pi integral 0 to infinity 1 by s into 1 plus s square into sin sx ds equal to 1 minus 2 by pi integral 0 to infinity 1 by s into 1 plus s square into sin sx ds. df by dx equal to 2 by pi integral 0 to infinity cos sx by 1 plus s square into ds. d square f by dx square equal to 2 by pi integral 0 to infinity s into sin sx by 1 plus s square into ds equal to f. d square minus 1 into f equal to 0. The solution is f of x equal to a into e power x plus b into e power minus x. Put x equal to 0 in 2 and 4. F of x equal to 1 and f of x equal to a plus b. Therefore, a plus b equal to 1. Also, from 4, df by dx equal to a into e power x minus b into e power minus x. Put x equal to 0 in equation number 3 and 6. df by dx equal to minus 2 by pi integral 0 to infinity ds by 1 plus s square equal to minus 2 by pi tan inverse s with the limit 0 to infinity. After applying the limit, we getting minus 2 by pi into pi by 2 equal to 1. df by dx equal to a minus b, therefore a minus b equal to 1. Then a plus b equal to 1 and a minus b equal to 1. After adding these two equations, we getting 2a equal to 0, then a equal to 0. Subtracting 2b equal to 2, then b equal to 1. Therefore, f of x equal to e power minus x. Example: if f of x equal to 1 for modulus of x less than a, 0 for modulus of x greater than a, and capital F of s equal to 2 into sin as by s, comma s not equal to 0, prove that integral 0 to infinity sin square ax by x square into dx equal to pi by 2. Solution: Parseval's identity states 1 by 2 pi integral minus infinity to plus infinity modulus of f of s square, that means capital F of s square into ds equal to integral minus infinity to plus infinity modulus of f of x square into dx, that is integral minus infinity to a modulus of f of x square into dx plus 1 by 2 pi integral a to infinity modulus of f of x square into dx plus integral a to infinity modulus of f of x square into dx equal to 1 by 2 pi integral minus infinity to plus infinity modulus of capital F of s square into ds. Then 0 plus integral minus a to a dx plus 0 equal to 1 by 2 pi integral minus infinity to plus infinity 4 into sin square as divided by s square into ds. Then 2a equal to 2 by pi integral minus infinity to plus infinity sin square as by s square into ds. Therefore, integral minus infinity to plus infinity sin square as by s square into ds equal to pi a. Therefore, 2 into integral 0 to infinity sin square as by s square into ds equal to pi a. That is integral 0 to infinity sin square as by s square into ds equal to 1 by 2 into pi a. Example: use Parseval identity to evaluate integral 0 to infinity dx by x square plus a square and integral 0 to infinity x square by x square plus a square into dx. Solution: let f of x equal to e power minus ax, then capital Fc of s equal to a divided by a square plus s square. The Parseval's identity is 2 by pi integral minus infinity to plus infinity modulus of capital F of s square into ds equal to integral minus infinity to plus infinity f of modulus of x whole square into dx equal to e power minus 2ax by minus 2a with the limit 0 to infinity. Therefore, integral 0 to infinity 1 divided by a square plus s square whole square into dx equal to pi by 2a square into 1 by 2a equal to pi by 4a cube. Therefore, integral 0 to infinity 1 by a square plus s square whole square into dx equal to pi divided by 4a cube. Also, capital Fs of f of x equal to s divided by a square plus s square. From Parseval's identity, 2 by pi integral minus infinity to plus infinity modulus of s divided by a square plus s square whole square into ds equal to integral minus infinity to plus infinity modulus of e power minus ax the whole square into dx. Therefore, 2 by pi integral 0 to infinity s square divided by a square plus s square whole square into ds equal to integral 0 to infinity e power minus 2ax into dx equal to 1 by 2a. Therefore, integral 0 to infinity x square divided by a square plus x square whole square into dx equal to pi divided by 4a. Example. Find the Fourier transform of f of x if f of x equal to 1 minus modulus of x, where modulus of x less than 1, 0 for modulus of x greater than 1. Hence, find the value of integral 0 to infinity sin t by t whole power 4 into dt. Solution. Given f of x equal to 1 minus modulus of x for modulus of x less than 1 and then 0 for modulus of x greater than 1. Capital F of small f of x equal to capital F of s equal to integral minus infinity to plus infinity f of x into e power isx dx equal to minus integral minus 1 to plus 1 1 minus modulus of x into e power isx into dx equal to minus integral minus 1 to plus 1 1 minus modulus of x into cos sx plus I sin sx into dx equal to minus integral minus 1 to plus 1 1 minus modulus of x into cos sx dx minus I into integral minus 1 to plus 1 1 minus modulus of x sin sx into dx equal to minus integral minus 1 to plus 1 1 minus x into cos sx dx plus 0 equal to 2 times of integral 0 to 1 1 minus x into cos sx dx. It's a even function, so the integral changes to 2 times of integral 0 to 1. After that, we using the udv formula uv minus integral v du equal to 2 into 1 minus x into sin sx by s with the limit 0 to 1 plus integral 0 to 1 sin sx by s into dx equal to 0 plus minus cos sx by s square with limit 0 to 1 equal to 1 minus cos s by s square. We getting this result after integrating and also applying the limits. Equation number 1. Parseval's identity states that 2 by pi integral minus infinity to plus infinity modulus of capital F of s square, that means whole square, into ds equal to integral minus infinity to plus infinity f of modulus of x the whole square into dx. Then 2 by pi integral minus infinity to plus infinity 1 minus cos s by s square whole square into ds equal to integral minus 1 to plus 1 1 minus modulus of x the whole square into dx equal to 2 times of integral 0 to 1 1 minus x the whole square into dx. It's a even function, so the integral converted into 2 times of 0 to 1. After integrating, we getting 2 times of 1 minus x the whole cube divided by minus 3 with the limit 0 to 1 equal to 2 by 3. We getting 2 by 3 after applying the limits. Therefore, integral minus infinity to plus infinity 1 minus cos s whole square divided by s power 4 into ds equal to 1 by 3 pi. Integral minus infinity to plus infinity 2 times of sin square s by 2 the whole square divided by s power 4 equal to 1 by 3 pi. Integral minus infinity to plus infinity sin power 4 s by 2 divided by s power 4 into ds equal to pi by 12. Put s by 2 equal to t. When s equal to infinity, t equal to minus infinity. When s equal to minus infinity, we getting t equal to infinity. Integral minus infinity to plus infinity sin power 4t divided by 16t power 4 into 2 into dt equal to pi by 12. Then integral minus infinity to plus infinity sin power 4t divided by t power 4 into dt equal to 2 pi by 3. Again, we converting the limit as even function. 2 times of integral 0 to infinity sin power 4 into t divided by t power 4 into dt equal to 2 pi by 3. Integral 0 to infinity sin power 4 into t divided by t power 4 into dt equal to pi by 3. Hence proved. Example. Find the Fourier integral of the function f of x equal to 0 for x less than 0, 1 by 2 for x equal to 0, e power minus x for x greater than 0. Verify the representation at the point x equal to 0. Solution. F of x equal to 1 by pi integral 0 to infinity, again integral minus infinity to plus infinity, f of x into cos s of t minus x into ds into dt equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f of x cos s of t minus x into dx plus integral minus infinity to plus infinity f of x into sin t minus x into dx into ds. Here we have written inside the bracket and also without bracket, which is separated with respect to x as well as ds. Whatever integrating with respect to x is written inside the bracket, without bracket we have written with respect to ds. Then equal to 1 by pi integral 0 to infinity, again integral 0 to infinity, e power minus x cos s of t minus x into dx into ds. Here also we have written in the bracket with respect to x equal to 1 by pi integral 0 to infinity. After integrating, we getting e power minus x divided by 1 plus s square into cos s of t minus x plus sin s of t minus x with the limit 0 to infinity into ds. After applying the limits, we getting equal to 1 by pi integral 0 to infinity cos sx plus sin sx divided by 1 plus s square into ds. Put t equal to 0, f of 0 equal to 1 by pi integral 0 to infinity ds divided by 1 plus s square equal to 1 by pi tan inverse s with the limit 0 to infinity equal to 1 by 2, which is true. Hence proved. Example. Express the function f of x equal to 1 for modulus of x less than or equal to 1, 0 for modulus of x greater than 1 as a Fourier integral. Hence evaluate integral 0 to infinity sin s into cos sx divided by s into ds and deduce the value of integral 0 to infinity sin s by s into ds. Solution. F of x equal to 1 by 2 pi integral minus infinity to plus infinity, again integral minus infinity to plus infinity f of t into e power is into t minus x into dt into ds equal to 1 by 2 pi into integral minus infinity to plus infinity into again the integral minus 1 to 1 e power is into t minus x into dt into ds. We change the limit using the cosine equal to 1 by 2 pi integral minus infinity to plus infinity, again integral minus 1 to 1 e power is into t minus x into integral minus 1 to 1 e power ist into dt into ds equal to 1 by 2 pi integral minus infinity to plus infinity e power isx into e power ist by s with limits minus 1 to 1 into ds. equal to 1 by 2 pi integral minus infinity to plus infinity e power isx into e power is minus e power minus is by s into ds equal to 1 by 2 pi integral minus infinity to plus infinity e power isx into 2 sin s by s into ds equal to 1 by 2 pi integral minus infinity to plus infinity 2 by s into sin s into cos sx minus I sin sx into ds equal to 1 by 2 pi with the integration minus infinity to plus infinity sin s into cos sx by s into ds minus 1 by pi integral minus infinity to plus infinity sin s into sin sx by s into ds equal to 1 by pi with integration 0 to infinity sin s into cos sx by s into ds 2 by pi integral 0 to infinity sin s into cos sx divided by s into ds. Therefore, integral 0 to infinity sin s into cos sx by s into ds equal to pi by 2 into f of x. That is integral 0 to infinity sin s into cos sx by s into ds equal to pi by 2 for modulus of x less than or equal to 1, 0 for modulus of x greater than 1. Put x equal to 0, then integral 0 to infinity sin s by s into ds equal to pi by 2. Hence proved. Inverse Laplace transform. Number 1. If L of f of t equal to capital F of s, then L inverse of capital F of s equal to f of t, where L inverse is the inverse Laplace transformation. Number 2. If capital F1 of s and capital F2 of s are Laplace transform of f of t and g of t respectively, then L inverse, that means Laplace inverse of c1 into f1, that means capital F1 of s plus c2 into capital F2 of s equal to c1 into L inverse of capital F1 of s plus c2 into L inverse of capital F2 of s. Important formulas. Number 1. We can call inverse Laplace transform or L inverse. Better we reading L inverse. L inverse of 1 by s equal to 1. Number 2. L inverse of 1 by s minus a equal to e power at. Number 3. L inverse of 1 by s power n equal to s power n minus 1 divided by n minus 1 factorial. Number 4. L inverse of s by s square minus a square equal to cos h at. Number 5. L inverse of 1 by s square minus a square equal to 1 by a into sin h at. L inverse of 1 by s square plus a square equal to 1 by a into sin at. Number 7. L inverse of s divided by s square plus a square equal to cos at. Number 8. L inverse of f of, that means capital F of s minus a equal to e power at into f of t. Number 9. L inverse of 1 by s minus a the whole square plus b square equal to 1 by b into e power at into sin bt. Number 10. L inverse of s minus a divided by s minus a the whole square plus b square equal to e power at into cos bt. Number 11. L inverse of 1 by s minus a the whole square minus b square equal to 1 by b e power at into sin h bt. Number 12. L inverse of s minus a divided by s minus a the whole square minus b square equal to e power at cos h bt. Number 13. L inverse of 1 by s square plus a square the whole square equal to 1 by 2a cube into sin at minus at into cos at. Number 14. L inverse of s divided by s square plus a square the whole square equal to 1 by 2a t into sin at. Number 15. L inverse of s square minus a square divided by s square plus a square the whole square equal to t in cos at. Number 16. L inverse of 1 equal to gamma of t. Number 17. L inverse of s square by a square the whole square equal to 1 by 2a into sin at plus at into cos at. Example 1. Find L inverse of 1 divided by s square minus 25. Solution. L inverse of 1 divided by s square minus 25 equal to L inverse of 5 divided by s square minus 5 square into 1 by 5 equal to 1 by 5 into sin h phi t. We just added phi in the numerator and denominator to get the formula for sin h at. Example 2. Find L inverse of s divided by s plus 2 the whole square. Solution. L inverse of s divided by s plus 2 the whole square equal to L inverse of s plus 2 minus 2 divided by s plus 2 the whole square equal to L inverse of 1 by s plus 2 minus 2 divided by s plus 2 the whole square equal to L inverse of 1 by s plus 2 minus 2 into L inverse of 1 divided by s plus 2 the whole square equal to e power minus 2t minus 2 into e power minus 2t into L inverse of 1 divided by s square equal to e power minus 2t minus 2 into e power minus 2t into t. In this problem, we just added plus 2 and minus 2 in the numerator. After that, it's a normal simplification and then we are applying the formulas. Example 3. Find L inverse of s square divided by s minus 2 the whole square. Solution. L inverse of s square divided by s minus 2 the whole square equal to d square divided by dt square into L inverse of 1 divided by s minus 2 the whole square equal to d square divided by dt square into e power 2t into L inverse of 1 by s square equal to d square by dt square into e power 2t into t equal to d by dt into e power 2t into 1 plus t into 2 into e power 2t equal to d by dt into e power 2t into 1 plus 2t. We have taken e power 2t as common equal to 2 into e power 2t plus 1 plus 2t into 2 into e power 2t equal to 2 into e power 2t into 1 plus 2t. We have taken the e power 2t as common in both the terms equal to 2 into e power 2t into 2 plus 2t equal to 4 into e power 2t into 1 plus t. Example 4. If L of f of t equal to capital F of s, then L of integral 0 to t into f of t into dt equal to 1 by s into capital F of s. That is, L inverse of 1 by s into capital F of s equal to integral 0 to t f of t into dt equal to integral 0 to t L inverse of f of s into dt. Proof. L of f of t equal to integral 0 to infinity e power minus st f of t into dt. L of integral 0 to t f of t into dt equal to integral 0 to infinity e power minus st into integral 0 to t f of t into dt equal to integral 0 to infinity into integral 0 to t f of t into dt into d of e power minus st divided by minus s equal to integral 0 to t f of t into dt into e power minus st divided by minus s into 1 by 1 with limit 0 to infinity minus integral 0 to infinity e power minus st divided by minus s into f of t into dt. Here we use the formula uv minus integral v du equal to 0 minus 0 plus 1 by s into integral 0 to infinity e power minus st into f of t into dt equal to 1 by s into L of f of t equal to 1 by s into capital F of s. Thus, L inverse of 1 by s into capital F of s equal to integral 0 to t f of t into dt equal to integral 0 to t L inverse of capital F of s into dt. Example 5. Find L inverse of 1 by s into s plus 1 into s plus 2. Solution. Let capital F of s equal to 1 by s into s plus 1 into s plus 2. Here we are applying the partial fraction. 1 by s into s plus 1 into s plus 2 equal to a by s plus b by s plus 1 plus c by s plus 2. We have taken this as equation number 1. After taking the LCM, we will get 1 equal to a into s plus 1 into s plus 2 plus b into s plus 2 plus c into s plus 1. Put s equal to 0 in equation number 1. We get 1 equal to 2a equal to 1 by 2. Then put s equal to minus 1 in equation number 1. We get 1 equal to b into minus 1 into minus 1 plus 2. Then 1 equal to minus b equal to minus 1. Put s equal to 2 in equation number 1. We get 1 equal to c into minus 2 into minus 2 plus 1. Then 1 equal to 2c. Finally c equal to 1 by 2. By 1 we get 1 by s into s plus 1 into s plus 2 equal to 1 by 2 divided by s plus minus 1 divided by s plus 1 plus 1 by 2 divided by s plus 2. We just substituted all the values here. Then L inverse of 1 divided by s into s plus 1 into s plus 2 equal to 1 by 2 into L inverse of 1 by s minus L inverse of 1 by s plus 1 plus 1 by 2 into L inverse of 1 by s plus 2 equal to 1 by 2 into 1 minus e power t plus 1 by 2 into e power minus 2t equal to, if we take the 1 by 2 as common, we will get 1 plus e power minus 2t minus 2 into e power minus t. Example 6. Find L inverse of s plus 2 divided by s square plus 4s plus 5 the whole square. Solution. Let capital F dash of s equal to s plus 2 divided by s square plus 4s plus 5 the whole square. Here we putting the integration with respect to ds on both sides. After applying the integration with respect to ds on both sides, integral f dash of s into ds equal to integral s plus 2 divided by s square plus 4s plus 5 the whole square into ds. After integrating the f dash of s, we will get f of s equal to integral s plus 2 divided by s square plus 4s plus 5 the whole square into ds. Put t equal to s square plus 4s plus 5. Then dt equal to 2s plus 4 into ds. dt by 2 equal to s plus 2 into ds. We have taken the 2 as common. Thus, f of s equal to integral 1 by t square into dt divided by 2 equal to 1 by 2 into minus 1 by t equal to minus 1 by 2t equal to minus 1 by 2 into s square plus 4s plus 5. L inverse of f dash of s equal to minus t into L inverse of minus 1 by 2 into s square plus 4s plus 5 equal to t by 2 into L inverse of 1 by s plus 2 the whole square plus 5 minus 4 equal to t by 2 into L inverse of 1 by s plus 2 the whole square plus 1 equal to t by 2 into e power minus 2t into L inverse of 1 by s square plus 1 equal to t by 2 into e power minus 2t into sin t. Definition of inverse Laplace transform as contour integral. Let capital F of s be the Laplace transform of a function f of t, t greater than 0. The contour integral L inverse of capital F of s equal to f of t equal to 1 by 2 pi I integral c minus I infinity to c plus I infinity f of s, that means capital F of s into e power st into ds, where I equal to square root of minus 1 and c greater than dou naught is called the inverse Laplace transform of capital F of s. Example 1. Evaluate L inverse of 1 divided by s plus 1 into s minus 2 the whole square. Solution. L inverse of 1 divided by s plus 1 into s minus 2 the whole square equal to 1 divided by 2 pi I integral c minus I infinity to c plus I infinity e power st divided by s plus 1 into s minus 2 the whole square into ds equal to 1 by 2 pi I integral c e power st divided by s plus 1 into s minus 2 the whole square into ds equal to sum of the residues is called equation number 1. S equal to minus 1 is a simple pole. S equal to 2 is a pole of order 2. Residue of f of s comma minus 1 equal to limit s tends to minus 1 s plus 1 into e power st divided by s plus 1 into s minus 2 the whole square equal to limit s tends to minus 1 into e power st divided by s minus 2 the whole square equal to e power minus t divided by 9. Residue of f of s comma 2 equal to limit s tends to 2 1 divided by 1 factorial d by ds of s minus 2 the whole square into e power st divided by s plus 1 into s minus 2 the whole square equal to limit s tends to 2 s plus 1 into t into e power st minus e power st divided by s plus 1 the whole square equal to 3 into e power st into t minus e power 2t divided by 9 equal to t by 3 into e power 2t minus 1 by 9 into e power 2t. Thus, L inverse of 1 by s plus 1 into s minus 2 the whole square equal to e power minus t divided by 9 plus t divided by 3 into e power 2t minus 1 by 9 into e power 2t. Convolution theorem. The convolution of two functions f of t and g of t is defined as f of t into g of t equal to integral 0 to 1 f of u into g of t minus u into du. Using convolution theorem, find L inverse of 1 divided by s plus a into s plus b. Solution. L inverse of capital F of s into capital G of s equal to L inverse of capital F of s into L inverse of capital G of s. Then L inverse of 1 by s plus a into s plus b equal to L inverse of 1 by s plus a into L inverse of 1 by s plus b equal to e power minus at into e power minus bt. F of t into g of t equal to integral 0 to t f of u into g of t minus u into du equal to integral 0 to t e power minus au e power minus b of t minus u into du equal to integral 0 to t e power minus au into e power minus bt into e power bu into du equal to e power minus bt integral 0 to t e power minus of a minus b into u into du equal to e power minus bt into e power minus of a minus b into u divided by a minus b with limit 0 to t e power minus bt into e power minus of a minus b into t divided by a minus b minus 1 divided by minus of a minus b equal to e power minus bt divided by a minus b into 1 minus e power minus at into e power bt equal to 1 divided by a minus b into e power minus bt minus e power minus at. Definition. An integral is of the form y of t equal to f of t plus integral 0 to t capital F of t minus u into g of u, that means capital G of u into du, is called the integral equation of convolution type. This equation can also be expressed as capital Y of t equal to f of t plus capital F of t into capital G of t. Example. Solve the integral equation y of t equal to 1 plus integral 0 to t y of u into sine t minus u into du. Solution. The given equation can be written as y of t equal to 1 plus y of t into sin t. L of y of t equal to L of 1 plus L of y of t into sin t equal to 1 by s plus L of y of t into L of sin t into 1 by s square plus 1. 1 minus 1 by s square plus 1 into L of y of t equal to 1 by s. S square divided by s square plus 1 into L of y of t equal to 1 by s. L of y of t equal to s square plus 1 divided by s cube equal to 1 by s plus 1 by s cube. Y of t equal to L inverse of 1 by s plus L inverse of 1 by s cube equal to 1 plus 1 by 2 into t square. Laplace transform. Introduction. Transformation. A transformation is an operation which converts a mathematical expression to a different but equivalent form. Example number 1. d by dx of e power x equal to e power x. Number 2. Integral e power x dx equal to e power x plus c. Laplace transform named after a great French mathematician Pierre-Simon de Laplace, 1749 to 1827, who used such transformation in his researches and the theory of probability. The powerful practical Laplace transformation techniques were developed over a country later by the English electrical engineer Oliver Heaviside, 1850 to 1925, and were often called Heaviside calculus. Uses of Laplace transform. Number 1. It is used to find the solution of linear differential equations, ordinary as well as partial. Number 2. It helps in solving the differential equations with boundary values without finding the general solution and then finding the values of the arbitrary constants. Conditions for existence. The Laplace transformation. Let a function f of t be continuous and defined for positive values of t. The Laplace transformation of f of t associates a function s defined by the equation capital F of s equal to integral 0 to infinity e power minus st into f of d dt. Here capital F of s is said to be the Laplace transform of f of t, and it is written as L of f of t, that is called Laplace transform of f of t or L of s. Thus f of s equal to, that means capital F of s equal to L of f of t. We can call this as Laplace transform of f of t. We can call Laplace transform of f of t as L of f of t. We no need to say again and again Laplace transform of f of t. It may be hard for someone. Better we calling L of f of t. L of f of t equal to integral 0 to infinity e power minus st f of t dt, comma t greater than 0. Example. State the conditions under which the Laplace transform of f of t exists. If a function f of t is continuous or piecewise sectionally continuous in a closed interval a less than or equal to t less than or equal to b and is of exponential order, then it is called Laplace transform exists. Exponential order. A function f of t is said to be of exponential order if limit t tends to infinity e power minus st f of t equal to 0. Define. Function of class A. A function which is sectionally continuous over any finite interval and is of exponential order is known as a function of class A. Important result. Number 1. L of 1 equal to 1 by s, where s greater than 0. Number 2. L of t power n equal to n factorial divided by s power n plus 1, where n equal to 0, 1 to etc. Number 3. L of t power n equal to gamma n plus 1 divided by s power n plus 1, where n is not an integer. Number 4. L of e power at equal to 1 divided by s minus a, where s greater than a. Number 5. L of e power minus at equal to 1 divided by s plus a, where s plus a greater than 0. Number 6. L of sin at equal to a divided by s square plus a square, where s greater than 0. Number 7. L of cos at equal to s divided by s square plus a square where s greater than 0. Number 8. L of sin h at equal to a divided by s square minus a square where s greater than modulus of a. Number 9. Laplace of cos h at equal to s divided by s square minus a square where s greater than modulus of a. Number 10. L of a into f of t plus or minus b into g of t equal to a into L of f of t plus or minus g into L of g of t. Example 1. Find L of t. Solution: we know that L of t power n equal to n factorial divided by s power n plus 1, where n equal to 0, 1, 2, etc. Laplace of t equal to 1 factorial divided by s power 1 plus 1 equal to 1 divided by s square. Here n equal to 1. Example 2. Find L of 1 divided by square root of t. Solution: we know that L of t power n equal to gamma n plus 1 divided by s power n plus 1, where n is not an integer. If n is not an integer, we have to use the formula gamma n plus 1 by s power n plus 1. If n is an integer, we have to use n factorial divided by s power n plus 1. That's what we used in the last problem. Then L of 1 divided by square root of t equal to L of t power minus 1 by 2 equal to gamma minus 1 by 2 plus 1 divided by s power minus 1 by 2 plus 1. Then we getting the answer square root of pi divided by square root of s equal to square root of pi divided by s. Example 3. Find L of sin 2t. Solution: we know that L of sin at equal to a divided by s square plus a square where s greater than 0. L of sin 2t equal to 2 divided by s square plus 2 square equal to 2 divided by s square plus 4. Here a equal to 2. Example 4. Find L of cos at plus b. Solution: L of cos at plus b equal to L of cos at into cos b minus sin at into sin b. Here we used the formula cos a plus b. Cos a plus b equal to cos a cos b minus sin a sin b equal to cos b into L of cos at minus sin b into L of sin at equal to cos b into s divided by s square plus a square minus sin b into a divided by s square plus a square. After simplifying this, we are getting the answer s into cos b minus a into sin b divided by s square plus a square. We just added these two things because the LCM is same. If the LCM is not same, we have to take the LCM and then we have to add. Example 5. Find L of f of t if f of t equal to e power minus t, comma 0 less than t less than 4, then 0 for t greater than 4. Solution: we know that L of f of t equal to integral 0 to infinity e power minus st into f of t into dt where t greater than 0 equal to integral 0 to 4 e power minus st into e power minus t into dt plus integral 4 to infinity e power minus st into 0 into dt equal to integral 0 to 4 e power minus of s plus 1 into t into dt plus 0. Then we are getting the answer using the integration formula e power minus of s plus 1 into t divided by minus of s plus 1 with the limit 0 to 4 equal to 1 by s plus 1 into 1 minus e power minus 4 into s plus 1. Example 6. Find L of f of t if f of t equal to t minus 1 the whole square, comma t greater than 1, then 0 for t less than 1. Solution: we know that L of f of t equal to integral 0 to infinity e power minus st into f of t into dt for t greater than 0 equal to integral 0 to 1 e power minus st into 0 into dt plus integral 1 to infinity e power minus st into t minus 1 the whole square into dt. equal to 0 plus t minus 1 the whole square e power minus st divided by minus s minus of t minus 1 into e power minus st divided by s square plus 2 into e power minus st divided by minus s cube. We have to apply the limit here 1 to infinity equal to minus of t minus 1 the whole square e power minus st divided by s minus 2 into t minus 1 into e power minus st divided by s square minus 2 divided by s cube into e power minus st integral 1 to infinity equal to 0 minus 0 minus 0. We getting these three zeros using the upper limit because e power minus infinity is 0. In all the three terms we having e power minus st. If we apply infinity there, sure we will get 0. That is called e power minus infinity equal to 0. Then we go into the lower limit. In general we know upper limit minus lower limit. So we putting minus and then into 0 minus 0 minus 2 divided by s cube into e power minus s equal to 2 divided by s cube into e power minus s. First shifting theorem. If L of f of t equal to capital F of s, then L of e power at into f of t equal to f of s minus a. That means capital F of s minus a. If L of f of t equal to capital F of s, then L of e power minus at into f of t equal to capital F of s plus a. Example 1. Find L of t power n into e power minus at. Solution. L of t power n into e power minus at equal to L of t power n s tends to s plus a. Then n factorial divided by s power n plus 1 because L of t power n equal to n factorial divided by s power n plus 1. S tends to s plus a. If we apply s plus a in s, we will get n factorial divided by s plus a whole power n plus 1. Example 2. Find L of e power t by 3 into t power minus 1 by 2. Solution. We know that L of t power 1 by 2 equal to square root of pi by s. Then L of e power t by 3 into t power minus 1 by 2 equal to L of t power minus 1 by 2. Then s tends to s minus 1 by 3. Then we getting square root of pi by s with s tends to s minus 1 by 3. The final answer is we getting square root of pi divided by s minus 1 by 3. Second shifting theorem. If L of f of t equal to capital F of s and g of s equal to, that means capital G of s equal to f of t minus a, where t greater than a, 0 for t less than a, then L of capital G of t equal to e power minus as into capital F of s. Important results. If L of f of t equal to capital F of s and c greater than 0, then L of f of t minus c into h of t minus c equal to, that means capital H of t minus c equal to e power minus cs capital F of s, where capital H of t equal to 1 for t greater than 0, 0 for t less than 0. Laplace transform of capital G of t equal to cos of t minus 2 pi by 3 for t greater than 2 pi by 3, 0 for t less than 2 pi by 3 equal to e power minus 2 pi by 3 s into s divided by s square plus 1. If L of f of t equal to capital F of s, then L of t into f of t equal to minus d by ds of capital F of s. If we have the t in the product, we have to use the differentiation. If t in the denominator, that means in the divide, we have to use the integration equal to minus capital F dash of s. Then again equal to minus 1 whole power n into f power n of s. Example 1. Find L of t into sine 2t. Solution. We know that L of t power n into f of t equal to minus 1 whole power n capital F power n of s. Then L of t into sine 2t equal to minus d by ds of L of sine 2t equal to minus d by ds of the formula for L of sine 2t equal to 2 divided by s square plus 4. After differentiating this term, we getting equal to 4s divided by s square plus 4 the whole square. Example 2. Show that integral 0 to infinity e power minus t into t sin t into dt equal to 1 by 2. Solution. We know that L of f of t equal to integral 0 to infinity e power minus st f of t into dt. Integral 0 to infinity e power minus t into t into sin t into dt equal to L of t into sin t with s equal to 1 equal to minus d by ds of L of sin t with s equal to 1 equal to minus d by ds of 1 divided by s square plus 1. This is the formula with s equal to 1 equal to minus of minus 2s divided by s square plus 1 the whole square with s equal to 1. We just differentiated the last step equal to 2 divided by 2 square equal to 1 by 2. Example 3. Find L of 1 minus e power t divided by t. Solution. L of 1 by t into f of t equal to integral s to infinity capital F of s into ds equal to integral s to infinity L of f of t into ds equal to then L of 1 minus e power t divided by t equal to integral s to infinity L of 1 minus e power t into ds equal to integral s to infinity 1 by s minus 1 by s minus 1 into ds equal to log s minus log of s minus 1 integral s to infinity equal to log of s divided by s minus 1. Here we use the formula log a minus log b equal to log a divided by b. We are applying the limit here equal to log of s divided by s into 1 minus 1 by s. In the denominator we have taken the s as common. One thing we have to note it very carefully. Till now we didn't apply the limit. In all the steps we have to write compulsory with limit s to infinity. Then equal to log of 1 divided by 1 minus 1 by s with limit s to infinity equal to 0 minus log of s divided by s minus 1 equal to log of s minus 1 divided by s. Initial value theorem. If L of f of t equal to capital F of s, then limit t tends to 0, f of t equal to limit s tends to infinity, s into capital F of s. Final value problem. If L of f of t equal to capital F of s, then limit t tends to infinity, f of t equal to limit s tends to 0, s into capital F of s. Example 1. If L of f of t equal to 1 divided by s into s plus a, find limit t tends to infinity f of t and limit t tends to 0 f of t. Solution. Limit t tends to 0 f of t equal to limit s tends to infinity s into 1 divided by s into s plus a equal to limit s tends to infinity 1 divided by s plus a equal to 1 by infinity equal to 0. Limit t tends to infinity f of t equal to limit s tends to 0 s into f of s equal to limit s tends to 0 s divided by s into s plus a equal to 1 divided by a. Example 2. Verify the initial and final value problem for the function f of t equal to 1 plus e power minus t sin t plus cos t. Initial value problem states that limit t tends to 0, f of t equal to limit s tends to infinity, s into f of s. L of f of t equal to capital F of s equal to 1 divided by s plus L of sin t plus cos t with s tends to s plus 1 equal to 1 by s plus 1 divided by 1 plus s the whole square plus 1 plus s plus 1 divided by s plus 1 the whole square plus 1 equal to 1 divided by s plus 2 divided by s plus 1 the whole square plus 1. LHS, that is called left hand side, equal to limit t tends to 0, f of t equal to 1 plus 1 equal to 2. And then right hand side RHS equal to limit s tends to infinity, s into 1 divided by s plus 2 divided by s plus 1 the whole square plus 1 equal to limit s tends to infinity 1 plus s into s plus 2 divided by s plus 1 the whole square plus 1 equal to limit s tends to infinity 1 plus s square into 1 plus 2 by s divided by s square into 1 plus 2 by s plus 2 divided by s square equal to limit s tends to infinity 1 plus 2 by s divided by 1 plus 2 by s plus 2 by s square equal to 1 plus 1 equal to 2. The initial value theorem is verified. Final value theorem states that limit t tends to infinity, f of t equal to limit s tends to 0, s into capital F of s. LHS equal to limit t tends to infinity 1 plus e power minus t sin t plus cos t equal to 1 plus 0 equal to 1. RHS equal to limit s tends to 0, 1 plus s into s plus 2 divided by s plus 1 the whole square plus 1 equal to 1 plus 0 equal to 1. Thus LHS equal to RHS. Transforms of unit step function and impulse function. Example 1. Define the unit step function. The unit step function, also called Heaviside's unit function, defined as u of t minus a equal to 0 for t less than a, 1 for t greater than a. This is the unit step function at t equal to a. It can also be denoted by capital H of t minus a. Example 2. Give the Laplace transform of the unit step function. The Laplace transform of the unit step function is given by L of capital U of t minus a equal to integral 0 to infinity e power minus st into u of t minus a, that means capital U of t minus a into dt equal to integral 0 to a e power minus st into 0 into dt plus integral a to infinity e power minus st into 1 into dt. The first term will get vanished because 0 into anything is 0. Then we integrate in the second term. We getting e power minus st divided by minus s integral a to infinity equal to e power minus as. That means we can also say e power minus s into a divided by s. Transform of periodic functions. Periodic. A function f of x is said to be periodic if and only if f of x plus p equal to f of x is true for some value of p and every value of x, the smallest positive value of p for which this function is true. For every value of x will be called the periodic of the function. The Laplace transform of the periodic function f of t with the period p is given by 1 by 1 minus e power minus ps integral 0 to p e power minus st f of t into dt. Example 1. Find the Laplace transform of the rectangular wave given by f of t equal to 1 for 0 less than t less than b, minus 1 for b less than t less than 2b. Solution. Given f of t equal to 1 for 0 less than t less than b, minus 1 for b less than t less than 2b. This function is periodic in the interval 0, 2b with period 2b. L of f of t equal to 1 divided by 1 minus e power minus 2bs integral 0 to 2b e power minus st into f of t into dt equal to 1 divided by 1 minus e power minus 2bs integral 0 to b e power minus st into dt plus integral b to 2b e power minus st into minus 1 into dt equal to 1 divided by 1 minus e power minus 2bs into e power minus st divided by minus s limit 0 to b minus e power minus st divided by minus s with limit b to 2b equal to 1 divided by 1 minus e power minus 2bs into minus 1 by s into e power minus st with the limit 0 to b plus 1 by s into e power minus st limit b to 2b equal to 1 by 1 minus e power minus 2bs. We taking the 1 by s as common, then minus of e power minus bs minus 1 plus e power minus 2bs minus e power minus sb equal to 1 divided by s into 1 minus e power minus bs into 1 plus e power minus bs into 1 minus e power minus bs the whole square equal to 1 by s into 1 minus e power minus bs divided by 1 plus e power minus bs equal to 1 by s into e power sb divided by 2 minus e power minus sb divided by 2 divided by e power minus sb divided by 2 plus e power minus sb divided by 2 equal to 1 by s into tan h into sb divided by 2. Conclusion. In this chapter, we have covered the following in detail: Laplace transform, inverse transform, linearity, shifting, transforms of derivatives and integrals, differential equation, convolution, and integral equations, Fourier series, integrals, and transforms, periodic functions, trigonometric series, Fourier series, forced oscillations, Fourier transforms.